Hello. In the last lecture, we mostly looked at shading simple objects like cubes. What if we have a more complex object like a sphere? In this lecture, we're going to look at principles of shading, and in the next lecture, we look at the implementation of the shaders. The projects related to this lecture are the shaded sphere 1 through shaded sphere 4. We have already seen the advantage of using polygonal models for our objects. Another advantage is that for flat polygons, we can significantly reduce the amount of work required for shading. We have three types of polygonal shading. 1. Constant shading. 2. Gouraud shading, which is based on intensity interpolation. And 3. Phong shading, which is based on normal vector interpolation. In flat or constant shading, each point on the polygon is assigned the same shade, as you see in here. Each polygon has one single color, and that doesn't change. So this is called flat shading or constant shading, and therefore we have uniform variables to represent these shades or colors. In smooth shading, each vertex has its own shade that the rasterizer can use to interpolate a shade for each fragment. Therefore, we need to have out type variables in the vertex shader that will go to the fragment shader as in type variables for interpolation. And here is an example that we have seen in one of the previous lectures. We have determined the colors of these 8 vertices, and all other colors across all the 6 faces of this cube have been interpolated by the rasterizer. So this is an example of smooth shading. In this lecture, we want to focus on smooth shading. How do we calculate a shade for each vertex in smooth shading? We can do it in 2 ways. In the first method, vertex colors become vertex shades and can be sent to the vertex shader as a vertex property or attribute, meaning we will have an in type variable in the vertex shader that gets linked with the application. Or number 2, we can send the parameters to the vertex shader and have the vertex shader compute the shade. Here is how we model a sphere. We have a tetrahedron. To start with, we subdivide it and connect the bisectors and normalize it so that the distance of the vertices to the origin is always 1. Kind of similar to the Sierpinski gasket and how we perform the subdivisions there. So here I'm showing where the number of subdivisions is 1, the number of subdivisions is 2, the number of subdivisions is 3. We are starting to see a real sphere. The number of subdivisions is 4. Is 5, and where the number of subdivisions is 6, and it's like a very good sphere that we are modeling in here. Now let's perform shading for the sphere that we modeled. In the Phong and modified Phong lighting model, we need to know the normals. In our first approach, we argue that each triangle is flat, and therefore it has a single normal, and it makes sense because for a viewer that's far enough, shades of a single triangle would be the same. So we get this. As you can see, the shade of each triangle is the same for all the points within that triangle. And that's the case for everybody here, except for where we have the specular highlights. As you can see, this is not smooth and does not really look good. So effectively, we have done flat shading with an exception of where we have the specular highlights. Now, what if instead of what we did, we calculate the normal analytically at each vertex of the triangles, and then we apply the modified Phong model to get a shade at each vertex, and then let the rasterizer interpolate the shades across the surface of each triangle. If we do that, we're gonna get this. This looks pretty good. It's remarkably smoother with the same number of subdivisions in our model of the sphere. And since we have a sphere, the normals are easy to calculate. The normal at each vertex is simply the vector that connects the origin to that vertex, as we proved before. So n is equal to the point itself. So this is smooth shading. Remember that we have just done 3 subdivisions, so this has been shaded pretty well for just 3 subdivisions. We observe this edge around this corner, which is known as the silhouette edge. It's just a silhouette of the object. The reason for its formation is discontinuities in the surface normals. And it turns out we need an awful lot of polygons to mitigate these discontinuities and to be able to get rid of the silhouette edge. Here we are seeing smooth shading for different number of subdivisions. At n equals 3 number of subdivisions, we are starting to see a nice looking sphere, and for n4 it should be acceptable for many applications, and for n6 it looks very good. The previous example is not general because we had a sphere and we knew the normal at each vertex analytically. What if we have a general polygonal mesh? Mathematically, there is no normal, for example, for a point like this, because there is a discontinuity. This point is shared between 4 polygons that have a slightly different orientation each. Gros, a French computer scientist, proposed that we can define the normal at a vertex to be the average of the normals of the polygons that share that vertex. So these 4 polygons are sharing this vertex. We know n1, n2, n3, n4 being the normals for each of these 4 polygons. So we add the normals together and divide them by the magnitude of their sum to normalize it. When we do that, we get a smoother rendering of the surface comparing to just simply shading each polygon with a different color. This is, in a way, an interpolation method for shading at the level of vertices. There is another interpolation method for shading that was proposed by Fong. Fong's shading can be applied to shade polygonal meshes. Fong said, I can do better than Gros did. What if I find the vertex normals and then I interpolate across the edges first and then across the entire polygon? For example, we know the normal at point A, we know the normal at point B. With this formula, we can find the normal at an arbitrary point along this edge, for example, point C. And then we take point C and another arbitrary point on this edge, point D, and we use this formula, another interpolation, to find the normal for an arbitrary point along this line. And this way, we can find the normal for an arbitrary point within the polygon, and we can cover the entire polygon with these normal calculations. Here, I can show the calculations better. We have n1 and n3. We interpolate between n1 and n3, and we find the normals with this formula for an arbitrary point across this edge. Likewise, we have n3 and n2. We interpolate between n3 and n2 with this formula, and we find the normal for an arbitrary point across this edge. Now we have the normal for 2 arbitrary points across this edge and this edge. We can interpolate between these 2 points with this formula and find the normal for an arbitrary point within this triangle, and we can continue doing so until finding the normals for all the points within this triangle, covering all the pixels in here. So now the question is, where are we going to do these interpolations? And it does sound a lot of work, right? The answer is no. In a shader-based graphics pipeline, where we can program the shaders like we do in WebGL, this isn't a lot of work for us. This is not difficult at all when we have programmable shaders like we do in WebGL. Let's look at step-by-step process for both shading methods. In grow shading, we first find the normals at a vertex to be the average of the normals of polygons that share that vertex. We then apply the modified Phong lighting model at each vertex. The calculated shades will be interpolated by the rasterizer across each polygon, and we are done. In Phong shading, we find the vertex normals first. We then interpolate vertex normals across edges. Then we perform another round of interpolation on edge normals across all the points within the polygon. And then we use the modified Phong lighting model and we apply it to each fragment, and we are done. Grow shading is per vertex and Phong shading is per fragment. In cases where surfaces change rapidly, grow shading will not work. It shows edges, and us human beings easily notice that because our visual system does edge detection. Versus with Phong shading, the object will look smooth. Phong shading requires much more work than grow shading though. But nowadays, we have programmable shaders. Every fragment is going to execute the fragment shaders. So nowadays, we can perform Phong shading in real time, which is per fragment. Remember that we need data structures in both grow shading and Phong shading to represent meshes so that we can find the normals appropriately. Here I just want to clarify something. We have the Phong lighting model, which was discussed in the last lecture, and we have the Phong shading model, which we covered today. These two concepts are two different concepts for different purposes. The purpose of the Phong lighting model is to determine how much light reaches a point on an object. It's also known as Phong illumination model or Phong reflection model. The model is empirical and based on physics of light. As we saw in the last lecture, we extended this model to modified Phong lighting model. And this model should remind you of this equation, which says the light that reaches a point has three components. It has the diffuse component, it has the specular component, and it has the ambient component. And these components need to be combined in order to get the final lighting for each point. On the other hand, the Phong shading model, the purpose is to shade a polygon in polygonal shading. So we must have a polygon to shade. What it does is it interpolates normals. So it's in a way an interpolation technique. It's also known as Phong interpolation. And after interpolation, it uses the modified Phong lighting model to find the colors. And this Phong shading model should remind you of a picture like this, where we perform two rounds of interpolation. The first round across the edges, like these two edges, and the second round across the polygon, like we do between point C and point D. And we can do these thousands of times to calculate the normals for all the points within the triangle. In the next lecture, we will look into the implementation of grow and Phong shading in WebGL.